Well, now that we've learned the technique for solving separable equations, we're going to look at linear equations. And a linear differential equation is one that we can write in the following form, and that is a first-order linear equation. It's dy dx plus some function of x times y is equal to f of x. Now we're going to assume that these aren't separable. In the case that they were separable, or that p of x equals f of x, then it would probably be easier just to solve this in terms of separation of variables. However, we're going to assume that p of x and f of x are not equivalent, and then we will apply this other technique. And we'll derive the technique here. It's not a proof that you are going to, or a derivation that you'll need to memorize, but it's helpful to understand what we're doing. So what we're going to do is we're going to define some function mu of x, and we're going to multiply that by both sides. So we get mu of x times dy dx plus mu of x times p of x y is equal to mu of x times f of x. Now, if we think about the left-hand side here and what that looks like, we see a function of x, mu of x, times dy dx plus mu of x times something else. And what it kind of looks like, it kind of has a resemblance of the product rule for differentiation, right? If we took the derivative, of mu of x and times y, then what that would be, and we're taking this derivative with respect to x, and I will write, just for sake of taking a derivative here, that y is also a function of x. Then what we would get is, well, we would say, okay, well, we'll take the first one, mu of x, and we'll multiply that by the derivative of the second one, dy dx. And then we will say, okay, well, now we'll take the derivative of the first one, so d mu dx, times the second, times y, or not mu, times y of x. And okay, well, now if we look at this left-hand side and we look at this right-hand side, well, the first two terms, this first part is easy, is the exact same. It's mu of x times dy dx. And we say, oh wow, okay, well, let's look at the second one. Well, here we have a y and we have a y, and if we let d mu dx equal the other portion here, the mu of x p of x, well, then these two will be equivalent. And so now we're on to something. And now what we see is we actually have created another differential equation, and this one is separable. So if we separate them, we'll get 1 over mu times d mu is equal to p of x dx. And now we can actually solve this. We take the integral of both sides. We get ln, absolute value of mu, is equal to the integral of p of x dx. And now we can put e on both sides, and the ln will cancel out, and we'll get mu is equal to e to p of x dx. Now, what we will notice here is, if this was technically an absolute value of mu, but if it doesn't really matter what the exponent of e is, whether the exponent of e is positive or negative, if we had e to the positive 1 or we had e to the minus 1, it doesn't really matter. This will always be greater than 0. So we can drop the absolute value sign here. It really doesn't matter. Now this is pretty remarkable. What we've shown here is that if mu is equal to e to the integral, and we have an integral in the exponent here, which isn't all that common, of p of x dx, then that'll satisfy this equation. And then we can rewrite this as, okay, well, we'll have d dx of mu times y, and these are both functions of x, and this will equal, well, we'll have to multiply mu times f of x. So then we'll have e to the integral of p of x dx times some function f of x that was over there. And now, for the last step, if we integrate both sides of this, so dx and integral of this dx, then what we'll have is we'll have mu times y is equal to the integral of e to the integral of p of x dx times f of x dx. And for our very last step, to solve for our solution, we'll have y is equal to 1 over mu times the integral of e to the integral of p of x dx times f of x dx. Wow. So we've created a formula now for our solution, and we've shown that if we can find this term mu of x, which we actually have a name for, mu of x we will call this is our integrating factor. Integrating factor is going to help us integrate this function. Integrating factor. Then what we can do is we can reduce the left-hand side to the derivative of mu, that integrating factor, times y, and then we can take the antiderivative of this derivative, and the derivative will cancel out, and what we'll be left with is an expression on the left-hand side that is very easy to solve for y. So when we are doing this, the first step that we're going to do is what we will do is we will find p of x. So whatever function is being multiplied by our y, and I will rewrite our form of the differential equation here, dy dx plus p of x times y is equal to f of x. Now it's important that we write it in this form. For example, if we had some sort of function like g of x that was being multiplied by dy dx here, it would be very important that we divided by g of x, divided everything by g of x here. That way we could write this in the form that we have above. So dy dx would then equal some new function, I'll write h of x times y, and then some new function here, and I'll write s of x. Now, so once we've determined our p of x, then, which is the function that's multiplied by our y, then what we will do is we will find our integrating factor. So mu will equal the e to the integral of p of x dx. So we will integrate p of x, and then we will set that as the exponent for e, and that will be mu. Then once we've done that, okay, so we will call this step solve for mu, or rather find mu. Find mu. Now once we've found mu, we can multiply everything by mu. So multiply by mu. And then our last step, we will integrate both sides. Integrate and solve for y. So those are the 3 steps, and we'll hop into an example here to see exactly how to do it. So for our first example, we will have the differential equation. We'll have dy dx, and this will be plus y over x equals 2. Now, so if we look at this, we'll realize that this is not separable. There's no way to separate the terms of x's and y's, and but we do realize that this is linear, and we know that p of x here, the function that's being multiplied by y, is equal to 1 over x. So if we want to solve for mu, then we will first take the integral of p of x and dx, and that will equal the integral of 1 over x dx, which is equal to ln of the absolute value of x. And we're not going to worry about our c here, because we're going to end up integrating this at the end, and then we'll deal with it there. So we have ln of the absolute value of x, and we know that mu is equal to e to the ln of absolute value of x. The e and the ln will cancel out, and then we'll have mu is equal to the absolute value of x. Nice. So now we know that the derivative with respect to x of mu times y is equal to the derivative or not the derivative, sorry, is just equal to our mu times whatever function we had on the right-hand side, which in this case is just 2. Now if we take the integral of the derivative here of mu times y with respect to x, and we take the integral here of, well, we can bring the 2 out front, and this will be mu is the absolute value of x dx. Then what we will find is we will say, okay, well, this is equal to mu times y, which is equal to 2 times the integral of the absolute value of x dx, and mu is equal to the absolute value of x. So you get y is equal to 2 over the absolute value of x times the integral of the absolute value of x dx. So let's think here for a second. We obviously know that x cannot equal 0. And we knew that from the start because we had this y over x, and if x equals 0, then it would be undefined. So, but it can equal all other values. So we had these two intervals, negative infinity to 0, and we had 0 to infinity, and these are open intervals, not including 0. So let's consider the first case here where our x is negative. If we graph the function y equals the absolute value of x, then what we get is we get this V shape here. It's a piecewise function. And we notice that this is y equals x, and this is y equals minus x. And together, this graph is the piecewise function of y equals the absolute value of x. So when our x is less than 0, we know that y is equal to minus x. So what we could do is we could say, okay, well, let's on this interval where x is less than 0, so x is less than 0, we have y is equal to 2. Well, our absolute value of x is just minus x times the integral of, well, minus x dx. And what this ends up equaling is 2, and the negatives cancel out, so x times the integral of x dx. Now on the interval from 0 to infinity, where x is greater than 0, well, we know that here our absolute value of x is just equal to x. So we get y is equal to 2 over x times the integral of x dx, which is equal to 2 over x times, well, we are just rewriting the same thing here. And what we find is that these two are actually the same. So we can drop the absolute value sign, it doesn't matter. So now we can actually compute this derivative, or this integral rather. So y would equal, well, that would be 2 over x times 1/2 x squared. And now the 2 and the 1/2 cancel out, one of the x's cancel out, and we have to add our plus c here, and we get y is equal to x plus c. And that is the solution to this differential equation. And we solve that by finding an integrating factor. Now, I hope this made sense to you. If you have any questions, please leave a comment below. And in the next video, we will include a couple more examples that are much more difficult than this, but they still use the same technique. And I'll see you in the next one. Bye.